Welcome AP Calculus to the last topic of Unit 10, which is representing functions as Taylor series as well as power series. So in this video we have three main goals, and so I've broke it down into three different examples. Our first is that we will extend our use of Taylor polynomials from a few lessons ago to creating Taylor series. We will then use that understanding of a power series we've done to create brand new series using different algebraic processes. And finally, we will bring in differentiation and integration into these power series as well. So without further ado, let's get into it. What you will see here on the screen before I jump into the examples are common Maclaurin functions, Maclaurin series I should say, for e to the x, sine of x, cosine of x, and then 1 over 1 plus x. These are the four most common power series and Taylor series you will see on the AP exam. So it is best to become familiar with either the series notation or the expanded form, or both of them, in fact, as you will see them oftentimes on free response questions as well as some multiple choice. So in the first example, we are going to find the power series for the function f as e to the x plus sine of x minus x. Now the directions don't have how many terms we're going to write, so what I'm just going to do for this first one is have kind of a loose expectation. We're just going to write everything out and just maybe write the first 5 to 6 terms until we start to see maybe some things that we're noticing as we're going through there. So the first thing I'm going to do is I'm going to take and write the Maclaurin series for e to the x. And again, I'm going to get those values from the table at the top of the lesson. So let's write out the first few terms. 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus, I'll write one more, x to the 4 over 4 factorial, plus dot, dot, dot. It would keep going on, but we're just going to leave it at the first 4. All right, let's put a plus because now I'm going to go and find the ones for sine. Again, I'm going to go up to the table and grab these values. So the first few are x minus x to the third over 3 factorial, x to the fifth over 5 factorial, minus x to the 7th over 7 factorial. We wrote 5 terms. Let's go ahead and write a fifth one just for this one, for fun. All right, plus dot, dot, dot. And then the final thing we have is, well, this is not one of our transcendental functions. This is just plain old x. So if you already have something as a polynomial, we don't need to write it in a series form because it's already in a polynomial form. So we'll just go ahead and write minus x at the end of it. Okay. So we've technically answered the question. Now what I want you to see here is we are going to look for some patterns. And so what are some patterns that we're looking for here? So let's use, we're going to use the pink, even though we're going to see right away that this negative x, and actually there's two different x's, we'll just take this one out here first. You will also notice that for any of the, I guess it's every other odd, is going to have a negative, that it's going to match its counterpart on the e function. So x to the third over 3 factorial will cancel with negative x to the third to the 3 factorial. And technically x to the 7th would cancel with x to the 7th here, but that's over in the dot, dot, dot section. Okay, so let's just write out the first few terms of what we've concluded here. So the 1, nothing changes. This x didn't change. Now let's go to the second power. We just have this x to the second over 2 factorial. We will no longer have a degree of 3 because both degree 3's cancel each other out. The next would be the degree of 4 over 4 factorial. Now, for the e, we're getting into the dot, dot, dots now. X to the 5th over 5 factorial is actually also located over here. So we would also have 2 of those in this situation. So it would be 2x to the 5th over 5 factorial. And then we'll just write a few more. Again, this is not realistic of an AP question. They may say, like, just write out the first few terms or be a multiple choice question. The goal of this first question is just for you to see a pattern. So we're going to say, all right, well, x to the 6 over 6 factorial, that's coming from the e function. There's no x to the 7th anymore. There would be an x to the 8th, and there would be 2 x to the 9th. So you can actually see that a pattern is starting to form, and we could keep writing these all day until we got an actual longer polynomial, but this one's going to be good enough. So final answer. Okay, so now that we have a gist of how this is working, let's actually take a look at it from the other direction, because now I have a series that has been manipulated from one of the original Maclaurin series, so we're going back up here to the beginning, And we're trying to see what we can match this up against, okay? So noticing when you look at the denominators, you have even factorials. That tells me that maybe this is a cosine function, but then when I look at the numerators, these are odd, which tells me it's a sine function. Now, the big thing to note here is that the only way we can manipulate these power series are with other variables. So I'm going to take a hunch here that these are going to remain the same, which means that this is almost the cosine. So what is cosine of x as a power series? Well, this is what it would look like. And again, I'm grabbing it from that table at the top of the page. So negative 1 to the n, x raised to 2 to the n over 2n factorial. So what you will notice here, and I'll highlight in green things that are matching exactly, are these. So we don't have to worry about those. What we need to concern our attention with here is notice the difference between this one and this one. And you will see that the series that I'm being presented with has an extra x to the first power multiplied into it. So 2 to the n became 2 to the n plus 1. So what that's telling me is that in order for this series, the one above, to match the cosine function is I'm going to have to multiply it by cosine. And so what that means is that x cosine of x, if I were to write that as a series, would now be written as, we'll still write n to the 0 to infinity. Now again, all of this stuff that I'm writing first is already the same. But now that we would have that pink x in there, we would have that pink x in there. We would have the x raised to the 2n. And again, we know that this is actually equal to x to the 2n plus 1. So what we've actually done now is we have found what the series is going to actually converge to. Converging meaning, what is it actually going to equal? Well, it equals x times cosine of x in this situation. So it can work two ways. One is, given the function, can you write the polynomial? Or given the polynomial, can you tell me what the original function was? So those are two different operations here in the first set of problems. All right, let's go to example 2. And in this next set, we are now going to take Taylor's series centered at 0. I don't know why that should say C there. And we're going to write out the first 4 non-zero terms and then the general term. Now, the best way to go about this, if you're not sure, is to actually write the original Maclaurin polynomial first. So in this case, writing e to the x. So this is going to be 1 plus x. And again, I'm writing the first 4 non-zero terms. So that's what I'm doing currently. And then we have x to the third over 3 factorial. So that's the first 4. So we'll go ahead and go plus dot 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 plus, and then our general term is x to the n over n factorial. Now, what makes this problem different is the exponent. The exponent is no longer just x, it is actually negative x squared. So what that means is that rather than writing x, when we go ahead and write our polynomial this time, every time we have an x, I'm going to leave it as a blank. So 1 plus blank plus blank squared over 2 factorial plus blank to the third over 3 factorial plus dot 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 plus blank to the n over n factorial. And so everywhere we see that blank, we can go ahead and plug in a negative x squared into each term. And so what we've done is we've taken a power series that we currently knew, the e to the x, inserted a different value into the function, and then was able to evaluate what it is from there. So that's going to be our final answer for all intents and purposes here. Now, looking down at letter B, and feel free at any point in this video, if you want to pause and try something before I go over it, please do so. All right, for this one, our original function looks like we're going to start with the power series cosine of x, and then we're going to do two different things to it this time. So let's write cosine, and we'll write those first couple terms. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 plus dot dot dot. And then we have our general term, which would look like this. Okay, so there's actually two things happening here. So what I'm going to do this time is I'm actually going to do them one at a time. So the first thing I'm going to do is recognize that everywhere we have an x, we're going to have a 4x inserted in place. So just like I did last time, I'm going to actually just go ahead and kind of set up the skeleton of this first. Okay. Oops, I wrote the x and I shouldn't have done that. That's a parenthesis to the 6. And then we have our dot dot dot. So we have this raised to the 2n over 2n factorial. So everywhere in there, I'm now going to go ahead and put a 4x in its place. So let's go ahead and do that. Okay, so we've got that taken care of. Now, the last operation that has occurred here, so we had the 4x inserted in, very similar to the E question we just did above. Now this time we're going to divide by x squared. So each thing gets divided by x squared. Now, dividing by x squared is the same as multiplying by 1 over x squared. So essentially, that would be over x squared. This would then be x squared, x squared, x squared, and finally 1x squared is there. Now, ultimately, this answer is done. We're essentially not simplified, but we have an answer. So in a lot of situations, you would stop here. But just because in this video, I'm showing you what we can do if we needed to simplify for any reason, this is what I would do, okay? So in this case, you will see that there's an x and there's an x squared. Those are actually going to cancel, giving me 4 squared, I should say. There should be a 2 right there. I lost that 2. So actually, the x squareds cancel out completely, leaving me with just 4 squared over 2 factorial. Again, I could simplify that if I want. Plus, this is 4 to the 4th times x to the 4th, so the 4 to the 4th is fine. That x to the 4th is going to cancel with the x squared, leaving me with just x squared in the numerator. So we would have this. So you might notice there's a new pattern forming. We have 4 to the 6. X to the 6 cancels with x squared, giving me x to the 4th in the numerator. And so what we can see that's essentially happening here, and we can actually write it out in the general term, the alternating part's not changing. The 2 to the n factorial isn't changing. But what's happening is the 4 is still being raised to the 2n each time, but the x to the 2n is being reduced by a factor of 2, which algebraically makes sense if you look at over here on the side. We have x to the 2n over 2. I can actually move this up top, and so this would be x to the 2n times x to the negative second, which would mean that we could write this as x to the 2n minus 2. So that would be my general term. Once again, in many, many situations on here, this middle problem that I wrote right here, this is going to be good enough, and you don't necessarily have to go as far. But if you wanted to be able to write it in its most simplified format, this would be what we would look for here. And you could even go further if you wanted to with the factorials, but again, not necessarily needed here. Okay. All right. We're going to pause on this video right now, and I'm going to have a second part here where we are going to go through the third part about differentiating and integrating series to create brand new ones.